All right, so for today's lesson, we are talking about and extending upon the idea that we talked about last time with degrees and radians. We're going to extend that idea to the central angle and the arc length of a circle. And the general concept of a central angle, hopefully that makes sense, it's literally called what it's called. It's because it's the angle which is formed from the center of a circle. And you need that information to be able to find the arc length. So that's our goal today. We're going to be able to determine the arc length and do that given the central angle and the radius, which you have to be given. But you also have to make sure that your central angle is in radians. That is going to be the important part. The formula is actually very, very simple. The formula for the central angle is going to be one of the easier formulas that you will have. I'm sorry, for the arc length, it's going to be one of the easier formulas that you have. The biggest thing is, again, is that you have to make sure that the information is given in the correct form. So a central angle, once again, is an angle formed between the initial and the terminal side created at the origin. So if we simply just put a dot here where the origin or the center of the circle would be, and then we create our initial side, and then we create some kind of a terminal side, the angle would go from the initial side to the terminal side. And what we typically label this angle is using a Greek letter, and that Greek letter symbol looks like this, kind of an O with kind of an extra line through it. It's called theta, T-H-E-T-A, theta. So again, it's kind of like a circle with a line horizontally through it. Basically, theta works just like any other variable, x, it's just that it's a Greek letter instead. The arc length is the length which goes from where the two radii hit the outside of the circle here. The arc length goes around the outside of the circle here in red. And we label that arc length S. I do not know exactly where the S specifically comes from, but that's what they call the arc length. All right, so the formula that you need, again, is very, very simple, and it involves the three things that we have here, and I'm going to go ahead and label that that's the radius of the circle right there. The arc length is the radius times the central angle. And again, the important thing is that the central angle must be measured in radians. Okay, and the reason it has to be measured in radians is because if you think about it, a radian has to do with the arc length, or the length around the outside of the circle. We did talk about that in a previous lesson, that's how the radian is actually developed. So that's why it must be in radians. But that's it. That's the formula. So using this is not too difficult as long as you have the correct information. So let's go ahead and translate this to some examples. So number one, we want to determine the arc length of a sector with a diameter, notice they gave us diameter in this case, of 24 centimeters and a central angle of pi halves radians. And they did give us the central angle in radians, so we're good there. The only thing that they didn't give us was that radius, which we need to be in, well, as a terms of a radius. Instead, they gave us a diameter. So our formula, once again, is S equals R theta. Since they gave us the diameter is 24, we know that the radius is half of the diameter, which makes the radius 12 centimeters. We know our central angle theta they gave to us is pi halves radians. And other than the fact that they use the word radian, we also know it's a radian because there's no degree symbol there. So if we want to find the arc length, it is simply 12 times pi halves. Okay, and we're going to leave this answer in terms of pi, which means we are not going to simplify the pi part. We are going to simplify the 12 over the 2 part, though, because we technically have a 12 divided by 2 here, which is going to give us 6, and then keep the pi. Now, if you had to do some kind of a decimal approximation, you would just plug in 6 times pi in your calculator, and you would get the answer. And don't forget, units are important here. Since we are measuring an arc length, that is a one-dimensional thing, so it's just going to be centimeters. So 6 pi centimeters is the length of the arc around the outside of the circle, with the central angle measuring pi halves, and the diameter, or the radius, excuse me, is 12 centimeters. All right, let's look at example number 2. This time it says determine the central angle. So now we're actually trying to find a different thing. They want us to find theta. They want us to get the central angle. They gave us the diameter is 12 feet, and this time they gave us the arc length, which is 3 pi fourths feet. So we want to express this, it says, as a fraction in simplest form. So again, we're going to start off with the same formula, S equals r theta, but in this case, we're solving for theta. We're solving for the central angle. So really what we need to do is we need to divide both sides of this by r. So if you divide both sides of this by r, the r's cancel out, and you get S over r equals theta. So do we have the S? Do we have the arc length? We do. S is 3 pi fourths. Do we have the radius? Well, not quite. They give us the diameter is 12 feet, but again, we know the radius is half of that. So that would give us a radius of 6 feet. So our theta is going to be S, which is 3 pi over 4, divided by 6. And when you divide fractions, because remember we can make 6 over 1 to make it a fraction, you multiply by the reciprocal. So this is going to be the same thing as 3 pi over 4 times the reciprocal of 6, which is 1 over 6, which is going to be 3 pi multiplying the top over multiplying the bottom, 24. That does reduce because 3 goes into both 3 and 24 evenly. So we get pi over 8, and that would be in radians because it is theta. So we have solved for the central angle, which is pi over 8. All right, let's keep moving. It says you try. If you want to pause the video and give it a shot real quick and see if you can figure this one out and then come back to the video, it's probably a good idea. I'm going to go ahead and keep going with it, but again, if you want to try it yourself, pause it and then start it back up again. So it says determine the measure of the central angle. So again, we're looking for theta of a sector with a diameter of 10 meters and an arc length of 10 pi thirds meters. So once again, S equals r theta, but we are solving for theta. Dividing both sides by r would give you S over r equals theta. So S is your arc length, which is 10 pi thirds. Write that a little bit better. 10 pi thirds. And r is going to be half of our diameter, which is 5 meters. So theta is going to be, write the theta a little bit better. Theta is going to be S, which is 10 pi thirds, divided by 5. Let's make it a fraction, make it 5 over 1. So that's going to be 10 pi thirds times the reciprocal, which is 1/5, which will give us a 10 pi over 15. And 5 goes into both 10 and 15, so that's going to reduce to 2 pi thirds. And that is your central angle. All right. Hopefully, if you tried that on your own, that's what you got. All right. If you haven't already, you can try number 4 on your own as well. But if you have, then let's continue on. So it says determine the arc length. This time we're actually looking for S. We're looking for arc length. Given that the diameter is 2 centimeters and the central angle is 270 degrees. Biggest thing there is they gave us the angle in degrees. It must be in radians, which means we have to do a little bit of extra work. We have to convert 270 degrees to radians. Eventually, this is a specific degree that you will get to know, and you'll see that in the second part of our videos here today. But for now, we're going to go ahead and use our conversion to be able to figure this out. So again, S equals R theta is what we start with. We know that our radius is going to be half the diameter, so that's 1 centimeter. And again, they gave us the angle in degrees, so we have to convert it. So let's do our conversion. Remember, we start off with 180 over pi. And that's going to equal, well, let's see, 270 is a degree, so it goes on top, over r, because we're going to solve for r. So we can cross multiply and divide, and we should be able to find this in terms of radians now. So we cross multiply, we should get 180 times r on one side, and then we get 270 times pi on the other side. And then to solve for r, we'll divide both sides by 180. So r is going to be 270 pi divided by 180. Okay, and we don't have to do this for the specific part of the problem, but we're going to anyway because we're going to simplify it. 270 and 180 do have something in common. They are both divisible by 90. You may not have seen the 90 right away, but you could definitely tell they're both divisible by 10, by 3 maybe. There's a whole bunch of ways you just have to keep going down, but they are both divisible by 90, which is going to give you 3 pi over 2. So now we have our radius, excuse me, our not radius, that's probably a bad choice of variables in this case because I do have a radius. So let's, I'm going to change my r in this particular example to be an n for radian. Not really sure if that's any better or not, but we'll go with n for radian in this case. So our radian measure here is 3 pi over 2. All right, well, it makes the last part of this very simple because it's S equals R theta. S equals R, which is 1, times theta, which is 3 pi over 2. Well, 1 times 3 pi over 2 is just 3 pi over 2. And this is in centimeters. So that's the measure of the arc. All right, this example specifically actually is going to play very well into what we just, what we're going to be going through in our second video when I come back with a second one here, and that's developing a unit circle. And it's called a unit circle because the radius of the circle itself is 1, which we will get to in much more detail in the second video. All right, a couple more examples on this video, and then we'll stop this one and come back with the second one. All right, a wedge-shaped slice is cut from a circular pizza. So just a normal cut of a pizza. The radius of the pizza is 8 inches, and the rounded edge of the crust of the slice measures 6.4 inches. All right, so let's just sketch what that is. So you've got the radius of the pizza. We're going to draw ourselves a nice little slice of pizza here. That was horrible. Try that again. There we go. Nice little slice of green pizza there. It says that the radius of the pizza is not 8 inches. So each one of these sides here is 8. It says that the rounded edge of the slice measures 6.4 inches. So really what that's given us is the arc length, the length around the outside, because if you obviously were to keep drawing that pizza, you know, all the way around, that was a horrible, horrible drawing, but you get the idea. That's a 6.4 measure of the arc. So what is the angle of the pointed end of the pizza slice? In other words, we're looking for this. We're looking for our central angle, the angle in between there. So again, S equals R theta. We are looking for theta, so dividing both sides by R would give you S over R equals theta. Did they give us the information in the correct form? Let's see. They gave us the radius, so that's good. And they did give us the arc length. Notice that there's no pi in the arc length. Remember, I told you there does not have to be a pi in the arc length. It's just 6.4, but since it doesn't say degrees, we know it's in radians, which is fine. So that's going to be very simple. We're going to plug in 6.4 for the arc length, and we're going to plug in 8 for our radius, and that will be our theta value. And I guess we can go ahead and try to reduce that a little bit. It's not really all that necessary. It doesn't, oh, it does say to the nearest tenth, excuse me. So we're going to have to plug that one into the calculator because it is going to ask us for that, and according to this, to the nearest tenth. So let's go one decimal place. So plugging 6.4 divided by 8 into the calculator. Oops, plug that in wrong. 6.4 divided by 8 into the calculator gives it, oh, well, how about that? Probably could have done that in my head. It's 0.8 exactly. And since it is the central angle, it is already in radians. So 0.8. There we go. All right, moving on. Number 6. Oh, this is a good problem. So it says that the diameter of the Earth is 7,917.5 miles. A U.S. space shuttle is flying at an altitude around 200 miles above the Earth. How far did the shuttle travel if the central angle from the Earth is 215 degrees? All right, so let's draw ourselves a nice little Earth here. And what it says is the diameter of the Earth, so all the way across through the center here, is 7,917.5 miles. Okay, we don't need the diameter to figure out arc length. What we need is the radius. So the radius, of course, is half of that distance. So I'm just going to put it out here that that's the radius. You will have to divide 7,917.5 divided by 2. I've already done that, and we get 3,958.75. So that's the radius of the Earth. But it says that the shuttle is flying around the Earth at an altitude of 200 miles. So there's another 200 miles out here that the space shuttle is flying. So here's your shuttle out here. Okay, really, really horrible drawing of a space shuttle, just a nice little dot. But it's traveling at that kind of a distance from the surface of the Earth. And it says that it goes around 215 degrees. So it is traveling around that way, 215 degrees, which basically is your central angle. Because if you were to then extend another thing out here, that angle in between there would be 215 degrees. 215 degrees, of course, is not in radians. They did not give it to us in radians, so we have to transform it into radians. So let's do that. Pi over 180 equals your radian measure. I'm going to use N again instead of R. Over 215, again, making sure the radian and the degrees match up left to right. So we're going to get cross multiplying 215 pi equals 180 times n, solving for n, divide both sides by 180. 215 over 180 is going to equal n. Okay, and that does reduce, but because of the fact that we're going to end up plugging this stuff into the calculator, I'm not so worried about reducing that at this point in time. If we didn't, then yeah, you probably want to reduce it. So we have our central angle measured in radians, and we have, for the most part, our radius. Now the radius, remember, is the radius all the way out to the shuttle, so it's this whole thing here added up. So the 3,958.75 plus another 200 would give us a radius measure of 4,158.75. So if we now want to find out how far the shuttle actually traveled around the outside of the Earth at an altitude of 200 miles above the Earth, that would be S equals 4,158.75 times our central angle of 215 pi over 180. And plugging all that stuff into the calculator should give us approximately 15,605.53 miles. That's quite a big distance that the space shuttle has traveled. And that's not even half of the Earth that it's gone around. But that's it. All right, one more example, and then we will call this one a video. Basically, same idea. The diameter of Mars. Let's draw our Mars. A little bit smaller than Earth. Since it's Mars, we'll do this in red. The diameter is 4,212 miles. Again, we're going to be more interested in the radius, which is going to be half of 4,212. That's 2,106. I do not expect you guys just to know that off the top of your head, but you can figure it out easily. And let's see, anybody who's seen the movie The Martian understands why this is, talking about Matt Damon being rescued and all that kind of stuff. The satellite tracking his movements is 155 miles above Mars, so there's another 155 miles out here as far as where the satellite is traveling. How far has the satellite traveled after orbiting 90 degrees? So the satellite has gone around the Earth, around Mars at a central angle of 90 degrees. So this is basically the same exact problem. You have to change 90 degrees into radians. I am not going to go through the process because we do have this one listed already. We've done 90 degrees before. That is pi over 2. It is half of pi because it is basically 1/4 of an entire circle. Again, this is an angle measure that you will get to know very, very well. And the only other thing we need is we need the radius, which in this case is 2,106 plus 155. That works out to be 2,261. So our arc length that the satellite has traveled is 2,261 times pi over 2. As an exact value, that would be 1,130.5 pi. That's just dividing 2,261 by 2 and then tacking on the pi. Or if we did it as an approximation where we multiply with using the pi button, then we would get 3,551.57 miles or so. All right, again, arc length, not terribly difficult, knowing what you're solving for, knowing the pieces that you need. Biggest thing is you need the radius, you need the angle, the central angle, but the central angle has to be in radians. That's the biggest thing. Problems like 6 and 7 are a little bit more advanced because they're adding some extra pieces, word problem type stuff, but same exact idea. All right, that is good enough for this video. I will come back with a second video and we will start to develop the unit circle.